Good morning, boys and girls. This is FE Peer Review. This is not a debunk video. This is not a peer review of another video. This video is just a quick look at the issue of scale on a flat map projection of our beautiful globe Earth and problems that arise when you try to go from a sphere to a flat surface. I got the idea to do this little video because this morning while I was blissfully sleeping through the night, there was a video posted by McToon and an interesting comment attached to it by Brian Leak. Now, the series McToon is doing I really like. It's called FEBS. And BS, by the way, stands for Black Swan, just to be clear about that. And this is number 4 in the series, in which McToon presents sort of a challenge or a logical, what do they call it? I forgot the name for it. Anyway, a challenge to flat earthers to solve a certain problem. And in this one, it's about flight paths. He's looking at a flight path from Sydney, Australia, to Santiago, Chile. On a flat surface, the shortest distance would be in a straight line, and he shows that on the screen here. And however, that is not the path that airplanes take when they fly nonstop from Sydney to Santiago. They actually follow a very different path, which looks like this. It goes from Sydney on the left, below south of New Zealand, fairly near the coast of Antarctica, and then across to Santiago. So that's the path that flights, commercial nonstop flights, actually take. And then back to this would be this straight line here from Sydney northward, just near Alaska, across the northwest corner of of the United States, down along the coast of Mexico through Central America, down to Chile. That would be the path of a straight line, the shortest path, on a flat plane. So McToon here is challenging flat earthers to explain why this is not the path that airlines take, whereas they take one that goes all the way south of New Zealand and quite close to the coast of Antarctica and around. So the comment is Brian Leak. He says, your FE map has the route length of 3 Australias, which puts it around 7,000 miles, give or take. Deceive much, McToon? Y'all getting desperate, lol. So let's see, 3 Australias. He's talking about this map here. Here we'll call our unit of measure 1 Australian, and it goes from the west coast to the east coast across Australia along a line of latitude. That's a 1 Australian. And yeah, it's about 3 to get from Sydney to Santiago. So let's see what's up with that. How far is it? And I bring this up because it's a great opportunity to look at what distortions are happening in this Mercator equidistant azimuthal projection, which is what this map is called. First, let's take a very quick detour and just take a quick look at projections. These are all a bunch of different projections, and these aren't all of them by any means. There are many, many, many more. But here's a bunch of different projections of a sphere onto a flat surface. We've got the one up in the upper left corner. You can imagine the right edge wrapping around and combining with the left edge to form a cylinder. That would be one approach. And of course, a cylinder is not a sphere, so there's going to be some distortions involved in that. Each one of these has its own particular combination of distortions. Each one of these was done for a particular reason, to show different things at different size, the same size, or different distances, the same distances, the same size. Anyway, like I said, these are just a few of the many. They're all fun to look at. My personal favorite is this one here, the McBride, because it gives you a nice, pretty decent comparison of the various continents at the same scale. The only real distortion happens across the top of Northern Europe here. There's a version of the McBride that actually has a split up here, which helps to reduce some of that distortion. The downside of the McBride is that the distances across oceans are completely off. Anyway, there's a bunch of them. Let's take a look at azimuthal projections in particular. The equidistant azimuthal is the map that McToon was looking at, and the one that's most commonly referred to by flat earthers. And it's called equidistant because it spaces these concentric circles the same distance apart. These circles represent lines of latitude. In this case, they're at every 15 degrees, and they're spaced at the same distance apart. Another way to do this would be to, instead of equidistant lines of latitude, would be equal area. So the areas of each sort of donut shape between these lines are correct. But as you can see, the lines are closer together here and farther apart up here. Let's take another quick look to relate all of this to the globe. Let me get my globe. Here's my globe. So this, of course, is a flat depiction of a globe. So you need to imagine that this is a real globe sitting in your room there on your desk, and you can refer to the distances on your real physical three-dimensional globe. So this little red line at the equator, that is a line that's following the circle of the equator, and it's 15 degrees. Each of these blue longitude lines are 15 degrees apart. So from the right end of the red line to the left end of the red line represents 15 degrees of longitude. And that amounts to, I think, if I'm going from memory here, roughly 1,600 kilometers. Now, from this intersection of these two red lines going northward, following a line of longitude, we come to 15 degrees north latitude. And it just so happens that this sort of vertical line here has the same length as the line at the equator. I've offset these red lines just so that they're easier to see, but from 15 north latitude to 30 north latitude, we've got another same length. 30 to 45 latitude, again the same length, and that goes on all the way up till 90. So each of these 15 degree latitude changes are exactly the same distance apart, and that's all a little more than 1,600 kilometers. Now, if we go over here and look at the green lines, this green line is the same length as this red line here. It's just another 15 degrees on the equator. And then if we move 15 degrees north latitude, this green line gets a little bit shorter. Another 15 degrees, it gets shorter. They get progressively shorter as they go up until it's 0 at the North Pole. Now, I just wanted to mention that the change, I don't have a good diagram for this, maybe I'll have a chance to slip that into the video. The change is not a linear change. The difference between the 0 and the 15 degree latitude in percentage terms is much less than the difference between say the 60 and the 75, or of course the 75 to 90 goes all the way to 0, so that's an infinite difference. Let's look at one more thing here before we move on. That's these two yellow lines I've drawn at the bottom. Now the first yellow line, the upper yellow line, that's at 15 degrees south latitude. And if you look at your desktop globe and compare that yellow line to the green line at 15 degrees north latitude, they'll be the same length. The same applies with the yellow line at 30 latitude south and 30 latitude north. Those will be the same length. Then it continues on down. 60 latitude south will be the same length as 60 north. So to recap, at the equator, each of these 15 degree changes is equal in length. The red line equals the green line here. As you go towards the north, following a line of longitude, the distance remains the same every 15 degrees. But as you go north or south, looking at the lines of latitude, the latitude lines get progressively shorter as you go towards the poles. So let's go back to the map with our azimuthal map here with our Australia and our South America. We've got one Australian, that's west coast to east coast across Australia. It's about 4,000 kilometers. I've repeated that 3 times, and that takes me over here to the west coast of South America. That line, if the flight path is going to follow the shortest route in order to save fuel and make more money for the airline, on a flat plane, the shortest route is a straight line. So that line would pass from Sydney across the Pacific Ocean north until it's somewhat near Alaska, and then it would cross over the west coast of the United States, down along the east coast of Mexico, and make its way down to the west coast of South America. That would be the shortest path on a straight line. Let's take a look at that path on Google Earth here. There's Sydney down at the bottom of the screen. The plane is heading north across the Pacific. Follow the red line. It's crossing south of Alaska, and then across the west coast of the United States and down east of Mexico through South America, Central America, and down to Santiago. That's the path of a straight line on the Mercator projection we were looking at. Now, if we look at the path that Muktoon showed as the shortest path on a sphere and the path that flights actually take, that's from Sydney on the left, south of New Zealand, fairly near Antarctica, and over to Santiago. That would be Sydney, south of New Zealand, approaching Antarctica, and then over to Santiago. And if we compare the lengths of those two paths, let's see, Sydney to Santiago, properties, measurement, 7,000 miles. Let's change that to kilometers. 11,000 kilometers. And if we look at the long route that goes up near Alaska and back down, properties, measurements, 24,000 kilometers. So it's more than twice as far to go via Alaska. Not a big surprise. You can see just by looking at the difference between those two. So back to our map. There's our map. There's the long red line represents the straight line path on a flat map. And we decided it measures 3 Australians. Now, just for giggles, I decided to add a couple more Australians to this map here. I thought we might as well look at a few other paths while we're at it. It doesn't have to be just this one flight. So I've copied the red line from Australia. I've copied my one Australian, and I've dropped it on the length is exactly the same. I've dropped it from over Europe, from the south of England. It extends all the way over to Bangladesh, past Bangladesh. So that's one Australian, and then I've added another one Australian that goes from the tip of South America up to the top of South America. This I've got to admit, I have never actually been to Australia, but it's my impression that the long direction of Australia does not take up as much space as going from the UK all the way across Europe, all the way across the Middle East, and all the way over past India. I don't think Australia is that big. Maybe if there's any Australians out there watching this, you can confirm that. I also don't think that the distance from the bottom of South America to the top of South America is the same as from one side of Australia to the other. So I think we have some distortions in this map here, and this is where we will see what they are. Let's go back and take a quick peek again at my globe here. As you recall, the distances between each of these latitude lines was the same. And the distances between the longitude lines get smaller and smaller towards each of the poles. Well, when we look at this map, the equidistant map is called the equidistant map because the latitude lines are equally spaced. The distances from one latitude line to the next following a longitude are the same. So that matches the globe. But where things get out of whack really fast is the distance of distance of a latitude line between longitude lines. Let me come up to the upper right corner here. You see where my mouse is circling? Let me draw in a few lines for us. Come on, where's my pencil? There's my pencil. I'll draw one from this point to that point. There's another one. And another one. Those would be 15, 30, and 45 degrees south. And here's 15 north, 30 north, and 45 north. So as you may recall on our globe, 15 north, the green line, was the same length as the 15 south latitude, the yellow line. The 30 north is the same length as the 30 south. When we compare that to this, 15 north is a great deal shorter than 15 south. 30 north is even shorter still than 30 south. They get farther, they get more and more out of whack, out of scale, as we move away from the center of the circle. And it's not just a linear change, it's actually got a curve to it. But I think that you can see now that it's these distances following latitude lines that are distorted. And since Australia is way out towards the edge of the ring, towards the edge of the ice wall here, and we're measuring along a line of latitude, we're maximizing that distortion. When we try to take that scale and apply it to, say, Northern Europe, we end up with an Australia that's as big as Asia and the Middle East and Europe combined, or we end up with an Australia that's longer than South America is. Clearly, that's not the way the world works. So there you go. Those are the distortions in the equidistant azimuthal map, and that's how you can see them. Like I was mentioning before, there's dozens of these projections, and each of them distorts in their own way. Quick and easy way to determine what kind of distortions are happening is to keep in mind the relative lengths of the longitude and latitude lines. Do that and you'll quickly see where the distortions occur.